Just, anybody have any questions on this? So this is just kind of a review. We talked about why bother to study welding. It's integrative, it involves many disciplines, and it kind of helps bring all the things together that you've learned in a number of engineering fields. That's one of the reasons I like it. I can work on anything I want. It's improved the size, the cost, reduced the cost, improved the size, increased the size, reduced the cost, and improved the reliability of life and life of things. It's used virtually everywhere. Did anybody come up with a largest standalone product? Think of anything? Okay. I mean, people used to come up with nails and stuff. One person came up with a cast iron frying pan. I think I told you one professor came up with an anvil. I have seen anvils about the size of this room, so anvils are pretty good choices. It's a large fraction of the manufacturing cost. I think this is what I was talking about at the end last time. It comes at the end of the process where the cost of scrap is high because you've already done everything else.
Anvils really can't be used by themselves unless you drop them on something.
That's true. But if you got a hammer, right?
But that's, you know, you need to cast something else.
Okay. So two parts. I mean, it depends on how you want to define this thing, right? The point of the exercise is actually to realize that welds are everywhere, joints are everywhere. Usually when students come up with something, you know, they said a fiberglass bath shower, you know, was one of the things they came up with. Well, it's large, but it's not very heavy. You know, it's kind of just a lot of paper, fiberglass. Anyway. So these things come in when the cost of scrap is high, and therefore people get upset about it. I think I also mentioned that there are many failures associated with welding, and in fact, I didn't talk about the Liberty ships, did I? Very briefly. Did I show you pictures of them? Yeah. No, I did. So you know you can see this guy. But the Liberty ships are an example. One of the things I've done in the past in this class, actually on the, I think part you'll see on the video is the Alexander Keelan disaster. Anybody know about the Alexander Keelan? It was an offshore platform, oil platform in the North Sea. Originally it was supposed to be a drilling rig. It had been built in a shipyard in France, and it had converted into a hotel out there. You know, basically a platform not for drilling, but a platform for people to spend the night in while they're working, because you work 3 shifts. You know, you work around the clock on these oil rigs. And they had a big storm come along, and in the storm the thing tipped over, and there were 230 some people. I think 130 some people lost their lives. And it turns out the whole thing was traced back to an improper weld on a sonar bracket. And it turns out they didn't even use the sonar bracket. It was for the drilling operation, and they never used this thing for drilling, so they never put the sonar system on this bracket. And it turns out what happened, those of you who have been in shipyards know that you have the welding group has some fairly tight quality control, and you have procedures and controls and people who are qualified. Well, in this French shipyard, they had that same type of controls for building the structure, but in the this bracket where they just they thought it was actually about a 16-inch diameter piece of steel pipe, but they thought they were just going to weld it to the leg of the vessel, and they considered that just be maintenance, something for the maintenance group to do. And the maintenance group didn't have all this QC stuff, and so they just went and got a piece of pipe from the shop. It turned out to be high carbon steel pipe. They welded it just like with any old electrode, no controls, no process, no control whatsoever, and they ended up getting a hydrogen crack. And from that little hydrogen crack, they got a fatigue crack, and it ran for about 20, 30 feet before it finally just ripped off one of the legs. And when you lose one of the 5 legs in a storm on an pentagonal rig, you know, it's not good. So it took it about 20 minutes to capsize. But anyway, there's lots of major failures that have been associated with welding, and we've talked about the fact that it's not completely fair to blame it on the welds. They usually put the welds at the corners, which are the most highly stressed locations. Many times we've done all kinds of fancy things and thermomechanical processing to improve the steel or the aluminum or whatever, the mechanical properties. And then we go and heat everything up and make a weld, which is nothing more than a small casting. Wiped out all that wonderful thermomechanical treatment, and you expect the weld metal to match the base metal. Well, you can't always do it. Another problem with welding, these are negatives, that's my symbol for negative, and positive is plus. Okay. It's often applied as an art or an afterthought. For example, it's not just welds, but joints. I remember when the space shuttle, which was the first space shuttle to Columbia? Challenger. I get them mixed up now. When the Challenger went, it was about 11 o'clock in the morning or whatever. I walked into my graduate student's office and they said, "Oh, did you just hear the space shuttle blew up?" And I said, "I bet it failed at a weld." And I was wrong. It failed at a joint. It was a rubber O-ring joint, and that joint had people have been looking at it for years, but it was sort of an afterthought of how to put this whole thing together. Welding is often performed manually, and therefore there's lots of human error. It takes skilled people, and if you ever looked at some of these people who are skilled people, you kind of wonder. In fact, whenever I go down an electric boat, and you see anybody at lunchtime, you go look at the parking lot or the parking garage afterwards, or during lunchtime, you see all these people sitting on their Harleys. I guess they're not supposed to be drinking beer, right? But whatever they're doing, right? So it can sometimes be a problem. They're complex processes. I always remember the story. I've got a lot of money out of Office of Naval Research from 1980 when I was a young professor, and they wanted me to get a bunch of people at MIT involved in welding, and I went to the guys down in the spectroscopy laboratory, the physicists, and they said, "Oh, there's nothing of interest in plasma physics and welding," so they didn't want to, even though I had money to give away, they didn't want any. And since then I learned, actually within a few years, I learned that was really just an excuse. The problem with plasma physics for welding is that it's such a complex area of plasma physics, the physicists will not touch it. Okay? They like to work with partially ionized plasmas or fully ionized plasmas, and partially ionized, partially ionized at the lowest level is like 1 or 2% ions in the gas, okay, or less. That way you can treat each ion as if it's surrounded by a bunch of neutral atoms, okay? A fully ionized plasma, you can treat it as if every ion is surrounded by other ions. But a partially ionized plasma, like 5 or 10% ionized, well, it gets to be really messy because it's, its nearest neighbors might be either ions or neutrals, and so it's very hard mathematically. So the real answer is it was too hard for the physicists to work on, okay? It's too complex. It's a real process, so therefore they don't want to work on it. Few people are educated in welding. We have about 2 schools in this country that actually have welding degrees. I'm not an advocate necessarily of welding as a discipline to study, but Ohio State University and Little Tourneau down in Louisiana are the 2 schools that offer 4-year welding engineering degrees. And so we turn out about 50 welding engineers a year in this country. In the former Soviet Union, in Kiev, they talked about turning out like 500 or more. Well, there's some politics for that, and then it depends on what you mean by a welding engineer, but certainly the majority of the people who study welding have never done any real welding in their lives. Their boss just says, "You're a welding engineer." That's what happened to me. I went to work for Bethlehem Steel, they said, "You're in the welding group." Okay? I had taken part of Professor Matsubuchi's course, but I had never welded. I didn't really have any training in welding, but that made me a welder. So.
You were in Buffalo, sir? Yeah.
No, I was in Buffalo. Yeah, Buffalo. That was a real plant. I did actually work in a real plant once or twice, but anyway. And the last reason is the ability to join something often limits the type of material we can use. For example, the Navy right now would like to go to lightweight ships for the high-speed ships for the littoral battlefield, and you like something light. Well, aluminum's light, but it's still, you like something even lighter than that. Here's lightweight aluminum, foamed aluminum. Can't be joined very well, but it would be great if you could make sandwiches out of that stuff, okay? But because it can't be joined, it's not widely used, can't be joined easily. I often say, if you're willing to pay the price, you can join almost anything, but price may be prohibitive. And we found ways to join that. It's just, it's going to be a real mess. It also depends on the industry you're in. We've been trying to build aluminum automobiles for, well, actually, we built aluminum automobiles in the 1930s. They built an all-aluminum Duesenberg. And Alcoa has been working with Audi for 15 to 20 years to build all aluminum vehicles. They sell them. I mean, I used to say in the early 90s, anybody can sell a $50,000 all aluminum vehicle. Can you sell one for $15,000? The answer is no. Nobody's selling an all aluminum vehicle for $15,000. Okay. But we know how to use aluminum in the aerospace industry, but that's because the value of a pound saved varies depending on the industry you're in. Okay, and well actually, the other stuff on material selection will go through that. But just to give you an idea, anybody know what the value of a pound saved in an automobile is over the life of the vehicle? Approximately. If you run 100,000 miles on a vehicle and you save 1 pound, it's about $2 a pound per auto. Okay? And for an aircraft,
Some fuel expenses you're talking?
that would be fuel expenses on the life of the vehicle. If you just plot, it's not too hard to do the calculation. You can compare the different weight vehicles and how many miles per gallon they get. There's a nice little trend line. You take the slope of that line and you calculate out over 100,000 miles. It works out to about $2 a pound is what you save. For an aircraft, anybody who's commercial aircraft, it's about $200 a pound. And actually for a military aircraft, it goes up to $1,000 a pound, depending on how high performance the aircraft is. Yeah.
It doesn't seem like a whole lot over the lifetime.
Per pound, it's a fair amount because they actually have vice presidents at commercial airlines like US Air or United have to decide how many magazines they're going to carry on the aircraft. Because on an aircraft, you're talking 100,000 hours of lifetime rather than 100,000 miles. So there's little differences here. But if you start thinking about it, well, the $2 a pound, I'll get to it in a second. It turns out, some of this is the material selection lecture, but the cost of the material is only about 10% of the fabricated cost, as fabricated cost. So if I can only spend 20 cents per pound for the material, that limits me in the types of materials I can use in automobiles. That's why you make automobiles out of steel. Now, with the recent increase in gas prices, this may have gone up to $3 a pound, okay? But it doesn't really matter, okay, so much. And maybe with this has gone to 300, I don't know. But and for a spacecraft, anybody have an idea? It's 10,000 is a good number, but for symmetry, I like to call it 20,000. If you originally, when they started building the space shuttle in the around 1970, the goal was to get the price of a pound of payload in space. So this is 100,000 hours. This is 100,000 miles. This is 100,000 hours. This is a pound of payload in space. Okay, whether it's reusable or non-reusable spacecraft. So you can argue they're different metrics, but they're the appropriate metrics for that vehicle in terms of what are you trying to do with the vehicle. Okay, you're trying to get life out of these two, and this one you're trying to get payload in space. And for every pound you can take out of the structure, you can put it into payload. Okay, and it costs you $20,000 a pound. Originally, when it was in the 1970s, the space shuttle was supposed to drop the price of a pound of payload from 10,000. So whoever said 10,000, that's a good number, down to 1,000. Well, it turns out if you actually look at all the costs of the space shuttle since its inception 35 years ago, it's been closer to 20 or 30,000. Okay, because those accidents really cost quite a bit. And then it turns out, you might know what it cost when they were running like 5 to 10 space shuttle flights a year, what it costs for the space shuttle program per flight. It's roughly $500 million per flight. Okay, so it's a little pricey. And when you're running the same program, of course at a reduced scale, and you're running one flight a year because you just had an accident, or you're running no flights a year, you get to $2 billion per flight, right? Because you have all that infrastructure you got to keep going. It's the same problem the Navy has, going from what they hoped was going to be a 600-ship Navy to what's the goal now, 250, 280 or something. You know, I mean, there's a certain economies of scale of having lots more ships, just like having more shuttle flights, you reduce the cost per flight and everything. So things start getting very, very expensive. In fact, this is part of the selection lecture, but the typical value of material in a manufactured product, the highest value of the material cost of the total cost of putting something in is a pipeline is about 30% for that steel pipe that goes in the ground, in something like the Alaskan pipeline. An automobile or an aircraft is about 10% of the cost of materials cost, and in semiconductors or spacecraft you might be down around 1%. So the actual cost of materials is not that great, and I don't think I put this one up before in this class. This is manufacturing cost for large-scale structures. Materials cost can be 10 or 20%. Let's say if we're talking a ship. The welding and joining costs can be equal to the cost of buying the metal. The other fabrication costs, machining, shaping, forming, but other than welding and joining, can be 10 to 20%. NDE, those of you who worked in a shipyard know that spend a lot of time on quality control, redoing it over and over, right? And arguing about it, what it means. G&A, hopefully you make some profit. Down here, be plus or minus 10% on the profit category. The point here, someone pointed out that they didn't realize how much painting costs. Well, in a shipyard, that's a repair cost. But some of these costs of fabrication work we do just far outshadow any materials cost. So they also put a limit on what types of materials we can use, as does welding, moldability of the material. Okay, so that's kind of introduction to why we should bother to worry about the course. I'm not sure if the guys in NAVC who put this together would agree. I'm not sure that this course is exactly what NAVC would design, because we're going to go through things like semiconductors and other stuff. And it's a typical MIT approach. It's a little different than you'll get out of most welding courses. This is actually a book by Peter Holcroft, who used to be Director General of the Welding Institute in Britain. I think I may have mentioned them very briefly when we talked about Liberty ships. After World War II, when the Liberty ships were cracking up, a guy, Richard Weck, was a young engineer, and he pedaled his bicycle from Cambridge University out to this little field in Abington, England, and decided this is where he wanted to build a welding institute. And the first problem he was going to work on is why the Liberty ships broke up. Okay, because it was known that they were welded structures. Did we talk about why they broke up? Because they were welded structures? I don't think we did. Okay. Well, anyway, there were two other places in addition to the Welding Institute. The British Welding Institute, outside of the Baton Institute in the Soviet Union, became the largest welding institute in the world, or it still is the second largest outside the Kiev. The Baton Institute in Kiev is larger, but and they were both built up for sort of political reasons. The British Admiralty wanted to know why these ships broke up, and they gave Richard Weck this contract to do it, and that got them started. The Baton Institute got started because Professor Paton's father, Professor Paton, is now well into his 80s. I was just asked to write a letter for him to receive some award. Didn't really write it, but anyway. But his father was very good at welding tanks together and getting them back to the German front, with the Russians. And so he was a hero of the Soviet Union under Stalin for re-welding tanks and stuff. And so it turns out they controlled all the research money that came out of the went into the Ukraine. So they did lots of money on welding. The British did lots of work on welding. Then the Naval Research Lab in Washington, D.C., a guy named Collini, who later was part of the Course 13, the Ocean Engineering Department. I think he may still be alive, retired down on the Cape. But if Collini's still alive, he's got to be 85 or 90. But he was the guy who developed something called ratio analysis diagrams in the Naval Research Laboratory to help us really understand fracture toughness and fracture energy, which is fracture energy, and fracture force, which is stress. And then the third place that did a lot of work on brittle fracture of steels was MIT. And Professor Cohen, who just passed away about a year ago, was the primary person there. But in any case, a typical welding book is going to be like Holcroft's book, and it will try to describe welding processes, and you guys got a handout of this. You don't have to try to read all this. But basically, welding process classification, he's got shielding method up here, and then down along the side, he has source of heat. So he's looking at the heat that's put in, and you can have zero heat, in which case you have a cold weld, and we do cold welding, okay? You could use mechanical processes, and he has shielding method, whether you're using a vacuum or inert gas or things like that. You've got a handout of that page. But basically, Holcroft doesn't really realize it, but there's some more. He's almost got the two reasons why things will join or will not join. And if any of you read chapter 16 yet, anybody read part of chapter 16? No? Okay. In chapter 16, I tell you the two reasons why things don't bond. In fact, two pieces of metal, in theory, the atoms, if I bring them in contact with each other, should want to bond. There's two things that prevent them from bonding. Obviously, these things don't stick together when I just won't push them together. Now, there are other things, like certain adhesives, and you put them together, and they seem to bond. And we'll talk about adhesives and why they work. But the first reason why things don't bond, well, actually, before I get into why they don't bond, let me talk about what happens when atoms come together. Okay? There's something called the Leonard-Jones Potential. Any chemists here ever heard of the Leonard-Jones Potential? This goes back to the early days of quantum mechanics and stuff. The Leonard-Jones Potential is the energy of attraction between two atoms. So if I've got, if I'm plotting the energy of attraction, a negative energy is an attractive energy, and a positive energy is repulsive. If this is one atom right here, this is the interatomic spacing, so I have another atom over here, and I would start with this atom and start bringing it closer and closer. There's no energy of attraction if they're far enough apart. Okay? I mean, if I got one atom here and another one on that side of the room, they don't even know each other exists. Okay? As I get them closer to closer, usually within 3 or 4 atomic distances, they will start to attract. And they either attract because of covalent bonding or ionic bonding. We'll go through these others in a little bit. But as they start to attract, the attraction gets stronger and stronger until eventually their nuclei, which both have positive charges, start to repel each other. So initially I either have covalent bonding or ionic bonding. In ionic bonding I have a positive and negative charge which attract, and they're pulled together. And then in covalent bond, or if they get too close, they start to repel. It gives me a minimum of energy. Minimum of energies tend to be most stable states, and that tends to be the equilibrium spacing, atomic spacing. If you go to some chemistry book, this is in chapter 1, figure 2. Okay, so this is pretty basic chemistry. And this is the same kind of Leonard-Jones attractive and repulsive component. So they plotted it. Here's the energy of the bonding. Here's the force of attraction. There's an attractive force. Let's say it's ionic bonding, and I got positive and negatives trying to come together, and this is just the, I'm sorry, this is the attractive force. The attractive force is just the positive and negatives, and the repulsive force is the nuclear repulsive force, and the sum of those two gives you a force curve like that. If you integrate f dot dx, then you will get the energy of attraction, which is just this. So I integrate this curve, the solid curve, and I get that curve. Okay, that's called the Leonard-Jones potential. And in fact, people have done that for lots of different types of atoms and bonding. And so here we have, now this is another chemistry book. In this case, they plotted the average bond energy and making the energy positive rather than negative, so they flipped the whole curve over, okay? But here, covalent and ionic have the strongest bonds. Metallic bonds have this is distance. Metallic bonds tend to have a longer range. They reach out further into nearest neighbors. Here's hydrogen bonding. Here's van der Waals bonding. If you've ever heard of these different types of things. Covalent, ionic, and metallic are what we call primary bonds. And they tend to have an energy, and I'll show you this in a second, on the order of 1 to 3 electron volts. Hydrogen bonding is a special case of van der Waals bonding, and that's basically an electrostatic bond. You have polar molecules. You have a molecule, if you have H2O. So here's your oxygen, and here's your hydrogen. And the hydrogen will get positively charged, and the oxygen will get negatively charged. And so when the water crystallizes and forms ice, the hydrogens will attach themselves to other oxygens, which are slightly negative charged, and there will be what's called a hydrogen bond there. Okay, it's just an electrostatic attraction because of the polar nature of the molecules. Some molecules aren't polar, okay, but many of them are. So van der Waals bonding and hydrogen bonding are much weaker. What they have up here, there's a little chart of this thing that talks about the range of the bonding in nanometers. If you want, I still like to think angstrom, so 10 nanometers is 1 angstrom, so this is 1.5 angstroms to 2.4 angstroms. Anyway, we're talking atomic scale distances here, and this is the energy, and this is in kilojoules per mole, but for me it's always easier to remember the energy in electron volts per atom. And electron volts per atom, primary bonds, ionic, covalent, metallic, are 1 to 3 electron volts per atom. Hydrogen's about 0.3, it's about 1/3 of the weaker of these primary bonds, and van der Waals is down even lower. So, if you bring two atoms together, and they are atoms that want to be together, like metal versus metal, they want to be together, that's why they form a solid. Okay? So if I stick them together, why don't they bond? Well, they don't bond for 2 reasons. The first one is, I have no rice. There's one over there. First reason is surface contamination. And the problem with surface contamination is it's everywhere. And we're worried about surface contamination on an atomic level. People have taken gold and cleaved it in an ultra-high vacuum system and put the 2 gold surfaces back together after they cleaved it, and they find they get extremely strong bonds. They weld it back together just by touching the gold to itself. But that doesn't happen in the normal atmosphere. And the reason is there is CO2, there's oil, there's water vapor, there's oxygen, all these things in the air. They did this with gold because gold doesn't oxidize. If I took a piece of chalk and try to put it back together, as soon as I break a piece of chalk, I've created a new surface. But it only takes 10 to the minus 8 atmosphere seconds. We call this the Langmuir. To contaminate that surface with one monolayer, okay, of contamination. It has units of atmosphere seconds. So if I'm at 1 atmosphere, like in this room, and I broke that chalk, it takes 10 to the minus 8 seconds for a monolayer of atoms to obstruct the surface. If I'm at 10 to the minus 8 atmospheres vacuum, it will take 1 second. Okay, if I'm 10 to the minus 16 atmospheres vacuum, it'll take 10 to the 8 seconds. Okay, and that's why in an ultra-high vacuum system, you can cleave gold, and as long as you put it back together within a minute or two, if it's very, very high vacuum, it will bond to itself. Okay, but it doesn't take very long in the world we live in, 10 to the minus 8 seconds. So if I stick that chalk right back together, it will actually rejoin, but I got to be very quick. Okay. Now the second reason, and actually Langmuir, there's a guy named Irving Langmuir who was a scientist at General Electric and spent his life studying surfaces. He won the Nobel Prize for some of the stuff he did 100 years ago on surfaces, studying surfaces, and that we named the Langmuir after him, and I'll show you some more about that in a second. But the second problem, if I had broken that chalk, I don't remember where I put my other piece, and I put the two back together, there's a problem. If I put them back together, I actually can hold that up to the light. I see light through there, right? They don't touch everywhere because they have rough surfaces. And I have to put them back, I would have to put them back perfectly aligned. Not only do I have to put them back in 10 to the minus 8 seconds or less, but I have to have them registered on an atomic scale in exactly the same location. So the second reason is that we have rough surfaces. And so that's what I use this for. Macroscopically, I might have something that looks very flat, and I put it back together, it looks like I got 100% area of contact, but on an atomic scale, I have something that looks like this. And I try to put it back together, and it only touches at a fraction of the spots. And we'll talk later about what fraction of those spots, but it's always less than 30%. It's typically 1% or even less. And so, even with the gold surfaces, when they took the gold in the vacuum system 50 years ago to do this experiment, then they cleaved the gold and they did it in a way so they had very flat surfaces, then put it back together, they only got about 30% of the theoretical strength. Okay? But that brings up an interesting question, is what is the theoretical strength of one of these things? Well, it turns out the theoretical strength of the Leonard-Jones potential, if I use that 1 to 2 electron volts, that's that around. If I take that Leonard-Jones potential, a typical equation for the atypical equation for the Leonard-Jones potential is minus A over R to the 6 plus B over R to the N, where these are some sort of constant. And this is your attractive force minus A over R to the 6, and the repulsive force is R to the N, where N is like 8 to 10. And you differentiate the energy, you should get the force, because if you remember, F dot dr, or the integral of force over distance, is equal to energy, right? Everybody remembers that from somewhere in physics once in your life. And if you take a typical value of a surface energy, which is 2.6 newtons per meter for two surfaces of iron, and you put them back together, and you calculate the area under that force R curve. I did this very roughly once because a student asked me to in this class, and I had never done it. But in any case, you get about 2 million psi. Well, we all know that's the strength of iron, right? Well, actually, it turns out it is the strength of iron in its native state. People in the 1950s made little iron whiskers, and they actually pulled these little iron whiskers, and those iron whiskers were absolutely perfect crystals, except they had one dislocation going up the center. That was in the same direction they were pulling, and so the dislocation didn't weaken the steel, the iron, and they measured about 2 million psi for those little whiskers. And at that time, in the 1950s, they said, oh, we're going to build new composite structural materials out of iron whiskers, and we'll have the strongest things in the world. Anybody know what people are saying today in the 1990s and 2000? what's going to be the strongest new structural material? Carbon nanotubes. You ever heard of carbon nanotubes? People are going to tell you they're going to build ships out of carbon nanotubes. Okay? $10,000 a pound for the carbon nanotube. Okay? I don't think you're going to be building a lot of ships because that's the material cost. That's not the as fabricated cost. Plus, this is a theoretical calculation. It turns out it may work as long as there are no defects in that structure. A carbon nanotube has this kind of hexagonal structure. If you're missing one atom, you've got a defect there. And all of a sudden, the strength may go down by a factor of 2. Okay? So rather than 2 million, you've got 1 million. If you have a bigger defect, it goes down to 300,000. So you're going to buy 10 carbon nanotubes, and you could actually take a piece of steel, aircraft quality steel, and make it, get 300,000 psi. Or 300,000, not KSI, 300,000 psi. Okay, so the carbon nanotube business, they say is going to be the structural material of the future, is they've forgotten about cost and they've forgotten about defects in the material. And in fact, we know that defects control the strength of the material. We learned that with the Liberty ships. I didn't pull the piece of paper for you. That's not bad. So if I take a piece of paper and I pull on the edge, it's got several pounds of resistance. If I put a defect in it, in fact, I'll put several defects in it of different size, and I pull it, it takes ounces, not pounds. And the biggest defect is the one that grew, and the smaller ones are insignificant compared to the big one. Okay? That's called the science of fracture mechanics. We've known it since 1925. We didn't really apply it until after World War II, and the reason the Liberty ships and the all-welded construction was a problem is because in the old days, we had riveted ships. The Titanic was riveted. And if a crack started in a plate, it ran all the way to the end of the plate, and then it stopped because there was nothing to drive the crack into the next plate, unless you had fatigue over a longer period of time. The Titanic had a problem because it was brittle steel, and the iceberg ripped, 5 compartments apart or something, and it could have survived if it had only ripped 3 or something. But it ripped 5, and that was too many to flood, and blah, blah, blah. In World War II, we started building welded ships. Why did we start building welded ships in World War II? Because they were cheaper. How long did it take from laying of the keel to floating the ship for the Liberty ships at the height of construction in 1944 when they really learned how to do it?
5 days?
5 days, something like that. Okay? Now that's just to float it. It may have taken another 6 or 7 days to outfit it, and put the top on, right? But 2 weeks was the total time from laying of keel to shipping that thing out with people on it. Okay? They had it down to quite a science. You couldn't have done that with riveting. Okay? You couldn't have built ships of the size and everything else. The problem is, if a crack starts in an all-welded structure, where does it stop? When it gets all the way around, okay? Or whatever, okay? So it's a problem. We've had pipeline failures where a little fracture starts in a welded pipeline and the crack runs 30 miles before it stops, okay? It's not a good thing. So, but you have the advantage of all welded construction is cheaper, lighter, more reliable, but if you have a failure, if you don't have something to control the crack, if you don't have crack something to stop the crack, in pipelines now, they'll actually put in a little 5 or 6 inch wide piece that might be twice as thick. So if the crack's running, it hits this brick wall and doesn't run so far, okay? And they learned that because they'd find cracks would run all the way up to a valve or something and stop, okay? Because now you have a big heavy piece of something to stop the crack. That occurs in gas pipelines more than oil pipelines. Anybody have a reason to know why that might be? Pressure? No, actually the pressures are almost the same. They're typically gas decompresses at a slower rate than a liquid. Okay? You guys know some of these things about compressibility in fluids. If you don't now, you're going to learn it in the next couple of years. But a liquid, the speed of sound in a solid or liquid is, what, anybody have an idea? 3,000 meters per second or something? Okay? In air, what's the speed of sound in air at sea level? That's pp. 343.6 meters per second. Okay, and now you get it right. It's 300 meters per second, but it's 10 times that. In a condensed phase, roughly. It may only be 2,000 in a liquid and 3,000 in a solid, but it's about that. Anybody have an idea why? It's 10 times as fast in a condensed phase as a liquid? Right? Right, distance between molecules is what you're saying, right? In a solid or a liquid, the distance between molecules is on the order of, let's say, 2 angstroms, right? In a gas like this, anybody have an idea how many atomic distances of the solid the gas would be apart? Equivalent, or how many angstroms apart? All you have to know is that it's 1,000 times, roughly 1,000 times. Natural gas is 800 times, but at room temperature, these are good little numbers to know. A gas expands by about a factor of 1,000, roughly. I mean, I happen to know natural gas at room temperature is about 800, okay? And it depends on what temperature you're at, because obviously the ideal gas law applies, and so for higher temperatures, it might be a factor of 2,000, but at room temperature, 1,000 is a good number. What's the cube root of 1,000? I can do that one in my head, folks. Okay, it's 10. So it's about 10 times the distance between the atoms. And the kinetic energy of the atoms at the same temperature, doesn't matter whether the gas or the solid or the liquid, they have the same kinetic energy, they have the same vibrational energy or speed, and therefore the gas only transmits sound at 1/10 the velocity because each atom has to go 10 times as far before it knocks the other one and tells it, hey, wake up, buddy. We just saw a pressure wave, right? See how that all works? So all this stuff they teach you at MIT is worthless if you can actually figure it out from basic principles of physics, okay? But that's not what they teach you. We teach you things like this, that the real strength of a carbon nanotube should be 3 million PSI, people tell us. Well, thank you very much. I bet if they actually get carbon nanotubes and measure them, they're going to be sadly disappointed on the actual strength, because they haven't thought about flaws that are in the material, okay? And the flaws will control the strength. Now, another thing people learned in the 1960s, they had the Mercury space shots. That was the first time we put someone in space. Anybody remember the name of the guy?
Alan Shepard.
Alan Shepard. And you know that because you live in Norfolk, right? Or Virginia Beach.
I went to the Naval Academy. And I rode. He was a rower.
Oh, okay.
First American space.
First American in space. I know his name. I remember his name because I graduated from high school in Virginia Beach, and the Civic Center in Virginia Beach used to be the Alan B. Shepard Civic Center because he spent some time, as many of you will, in the Norfolk, Virginia area. It's hard to avoid it. In any case, so Alan Shepard, on the first Mercury shots, they used for their little, carbon, or for the rheostats and stuff, they use graphite as a lubricant. We all know graphite is a lubricant, right? Except unfortunately, when they did things, these flights were short, because when they got up there, they found everything was sticking up there in space. Because it turns out graphite is not a lubricant in space, it becomes an abrasive, okay? And so, NASA, having lots of money back then, because they weren't dropping things out of the sky. Actually, they dropped things out of the sky fairly regularly. That's an interesting story. Richard Feynman was on the Challenger Commission, Space Shuttle Challenger Commission, to figure out why and NASA had done this big fault tree analysis. It's sort of like the carbon nanotube strength, okay? Being a fiction. NASA had done this thing showing that there was a 10,001 probability, there's only 1 in 10,000 liftoffs would you ever expect a failure on a space shuttle. They had this nice fault tree analysis and probabilities, but someone had estimated these probabilities, which means they just pulled it out of the air, right? And the numbers came out to 1 chance in 10,000. Well, Feynman looked at all the rocket launches since Werner von Braun came over here to start shooting off rockets, and he found that 4% of them had failed on liftoff, and on boost stage on liftoff. And he found this was the 25th shuttle flight. Okay. Cheating with statistics, right? As Israeli said, there's lies, damn lies, and statistics. Anyway, so NASA, after, anybody know the second person in space? That's real trivia. Gus Grissom. You guys weren't born then, I was. Okay. Anyway, so after Shepard and Grissom, NASA started funding a bunch of research, and so this is an ASTM spec. It's out of print, but it was published originally in 1967. So this is a symposium of adhesion or cold welding of materials in space environments. And what NASA did is they found all kinds of things that they never thought would stick together when they get up to space, where these things were sticking together. And this is a crystal structure of graphite. Anybody know how I can tell? The atoms are black, right? Carbon. So this is carbon.
A little tag on
That too. The little tag says graphite. But I didn't read it. I knew the atoms were black. Anyway, it has a hexagonal crystal structures, hexagonal close packed for all you material scientists. You can see these planes of atoms, and on Earth, those planes of atoms just slide over each other. That gives the lubricity for the graphite. So you go stick it in their locks, and the heat turns a lot better, right? But it turns out the bond, the Leonard-Jones potential between carbon-carbon bond says they should have a very strong bond. And in fact, they do. What gives it the lubricity on Earth is a layer of oxygen absorbed here. Carbon and oxygen have an affinity for each other. That's why they form carbon monoxide and carbon dioxide. So on Earth, at atmospheric pressure with 0.2 atmospheres of oxygen, you would get a layer of oxygen on this one, and the one next to it would also have a layer of oxygen on it. So you're really sliding on carbon monoxides, okay? And they don't have a very strong high surface energy. If you go through the Leonard-Jones calculation, they actually work quite well. You get up in space where you don't have a lot of oxygen, it turns out the strength of that bond was not so great. You'd actually just suck off the oxygen. And actually, I had a student, Dan Reese, who a couple of years ago retired. He was in your program back in 1983. And Dan did a thesis for me on welding of titanium. And he was welding the titanium in a glove box with argon, and we were at 10 to the minus 16 atmospheres of oxygen. We were using liquid argon to fill up this glove box and titanium together to burn up all the oxygen. And he was using a little dust buster, okay, a little hand vac. And he came to me one day, he says, Professor, I've had to replace the carbon brushes in this thing 5 times. They only last about 10 minutes. I said, well, Dan, that's because you got carbon brushes, and when you get rid of the oxygen, the carbon brushes were actually sticking to things. They weren't acting as a lubricant on the motor, okay? So things will stick together, and so NASA funded a bunch of basic research, and that's what this thing is about. And they're studying what they expect, because they realize this is the lack of oxygen. It was what keeps the dust down on the moon, okay? Because the particles, the silicate particles, the rock particles, even before they got to the moon, when they wrote this, would stick together because there wasn't as much oxygen around. There wasn't as much water vapor. And they don't get coated with that contamination. Just further proof that surface contamination is what keeps things from bonding together. So if any of you are really interested in studying something like lubrication technology is just the opposite of welding, if you get back to the fundamentals. In lubrication technology, you're trying to find something that contaminates the surface, okay? In welding, I'm trying to find some way to decontaminate the surface. And so if I go back to good old Peter Holcroft and his little plot where he's trying to figure out how to classify cold pressure welding, thermocompression bonding, hot pressure. This is no heat on there going across here. Just mechanical, explosive welding. He's got heat sources of thermochemical, electric arc, radiant energy, which is lasers. These are different ways of heating. And then he has shielding, gases, fluxes, inert gases. Fluxes are basically just chemical ways to try to clean the surface. Well, if we go back for all the part of this course that I'm going to lecture, we're going to keep these two things in mind. When we look at adhesive bonding, we're going to see how these apply. When we look at soldering, we're going to see how these apply. We look at brazing, which is just a variant on soldering. Okay, but right now we're going to start on cold welding, so far as that goes. And people say, why do you want to study cold welding? We don't cold weld chips together. That's true, you don't. But in fact, we make more cold welds in the world. Now, a cold weld, usually if you're doing arc welding, a cold weld is not a good thing, okay? But we do more thermocompression welding, or make more thermocompression welds than any other type of weld in the world. Probably than all other welds combined. Anybody have an idea of what product uses hundreds and hundreds of thermocompression welds?
PVC?
PVC is hundreds and hundreds and thousands, but actually it's trillions. But that is a semiconductor chip. Okay? Now this one actually is soldered, but I don't have one that's thermocompression welded. But we will get to it and study it. And that's not very well focused. But anyway, this would be the silicon chip in here in the center, and these are the bonds going around it. But they will typically, and this has 400 inputs and outputs, so it has to have 800 bonds on one chip. And if this is the silicon chip sideways, and this is your substrate, which would be aluminum oxide with a little copper pad, typically, might be a gold pad, and they will run a gold wire, and this thing will have a little aluminum pad deposited on it. They will run a gold wire about 25 microns, 1/1000th of an inch, and they will just squeeze it into the surface. And it'll make a little clip like that. We'll talk about it later. But for a, that was a Pentium, original Pentium, kind of old, about 10 years old. But you might have 800, 1,500 bonds like that on every chip. And if one of those is bad, it's junk. Okay? Have to have very high reliability, and it's basically a cold weld. You're making it by pushing two things together at the time to weld it together. One example, we do actually a fair amount of cold welding. This is a, and we don't have time to pass it around, I'll pass it around tomorrow. But this is a cage for some part of the transmission in a GM automobile. But in this case, it's steel, but it's got a layer of aluminum on it. Okay, if you look on the inside surfaces, you'll see the dark gray is the steel, and you'll see the silvery stuff is the aluminum surface. That's a nice. The aluminum makes a nice bearing surface, and in fact, most of the bearings in an engine, the rod bearings and the main bearings on the crankshaft, typically are the same type of aluminum to steel cold bond. They just take a piece of a sheet of steel or a big long roll of steel, and they take a big long roll of aluminum. They clean them as well as they can, typically an acid clean and a surface wire brush. They actually roughen up the surface for reasons we'll talk about. And then they squeeze them together with tremendous pressure and actually start rolling them and extending them and making a joint. Now, it's not a perfect joint, but it's good enough for the bearings. Another example of a bimetallic, there's a company down south of here, used to be part of Texas Instruments, and Cecil Green, who was an MIT grad in 1925 in geology, went to Texas in the oil fields. He was a geology grad. He went down there and he bought a little company that was making little instruments. It was a company called Texas Instruments. Okay, the Green building here, the big tall building, is named after Cecil and Ida Green. And if I take, they used to, down here in Metals and Controls, they used to make bimetallic strips. We should have a thermostat somewhere in this room, and every thermostat has got a bimetallic strip. If I heat up a bimetallic strip, they expand at different rates. Doesn't matter which side, it always bends in one direction because the coefficient of expansion is different. Okay? If I cool it off, it will slowly straighten itself out. This is the principle of most thermostats in your homes. Basically, you have a bimetallic strip and it moves with the temperature in a very predictable way. People use these things also, cold bonding, for cladding to get better corrosion resistance. Back in the early 1980s, it actually used to be able to say you could go look at minivans, and you could see in the 1980s through 1990s, you could see the history of cold welding for bumpers in minivans. Chrysler came out with the minivan in what, early 80s, 83 or something. But automobiles quit having chrome bumpers about that same time. Anybody know why? Hexavalent chromium, Aaron Brockovich, right? It's a carcinogen. And everybody was worried about the EPA. People had learned that hexavalent chromium was a very potent carcinogen, and no one had the environmental controls in their chromium plating shops. And all the automotive companies had to quit chrome plating their bumpers. And so the oldest minivans were aluminum bumpers with a rubber strip. They didn't do very good. Okay, the aluminum's not that good of a crash protector. At least not in the 1980s version of it. And but the first minivans had aluminum bumpers because people were used to having a shiny metal, and that was the best they could do. Then they started going to plastic bumpers, which is what they still do in a lot of them. But then the Ford Explorer around 1990 came back with chrome bumpers. There were a few vehicles that were still designed with chrome bumpers, and Metals and Controls down here went from being a $100 or $200 million a year business to nearly $1 billion business in the late 80s, because they were putting stainless steel, cold welding stainless steel to carbon steel, so that they could make their chrome bumpers. They couldn't chrome plate them anymore. They had to make a bimetallic bumper, which was fairly expensive, but they had already designed these vehicles until they got into the next design phase. So you could actually see this material substitution by looking at the automobiles. In the 1980s, or in the 1990s, the Ford Explorer came out in the early 90s, had chrome plated bumpers again. And why? Because Ford had bit the bullet and built, I don't know, probably spent $500 million or $1 billion to build an environmentally safe chromium plating plant. You know, basically robots and not very many people and all kinds of controls for the atmosphere, the air, and everything. So you can actually look at, I used to just, kind of say, look at bumpers on minivans, and you can actually see the history of getting chromium out. Can't use plating, go to aluminum, then they go to clad, cold welded metal, then they actually went back to chromium plating because it's the cheapest once you had a plant that was environmentally safe to do it. Okay, I'll see you tomorrow.
I work with Dan.